Aloha, friends. It's a pleasure to welcome all of you to a place that we love. And one of the questions you should be asking is why in the world are two professors from landlocked Utah here in Hawaii visiting with you about marine systems? And we've been working with collaborators here in Hawaii for a little over a decade, trying to help Native communities address issues related to the environment. And so much of what's happened has been beautifully opportunistic. I had a colleague that I was hired with at BYU in Provo, Utah, who grew up on the island of Molokai, and a number of his friends were involved in a Native Hawaiian group called Ainamamona. And Ainamamona took over the management of a watershed. And they had questions that they wanted answered that could only be addressed using some high precision mapping. And so my dear friend, who's now president of the BYU Hawaii, the branch campus on the north side of Oahu, invited me to come and participate in this work. And so we started working with Ainamamona and their organization a little over a decade ago. Before too long, we recognized that we needed other collaborators involved. And a few years ago, we had a graduate student join my lab who grew up on the island of Oahu here in Honolulu. And his father was one of the main navigators for the Polynesian Voyaging Society. And we started to recognize the intersection between some of the things that we were employing using unmanned aerial vehicles to do mapping and what was happening with the Polynesian Voyaging Society as well. And so we're going to talk in great depth about some of the insights that were developed by Polynesian voyagers, and they are not original to us. And we appreciate the work that was done in tutoring us from Mark Ellis, Kalai Ellis, and Walter Riddy. So what we're going to do is start, and I'm going to talk a little bit about the background and history of navigation in Hawaii, and some of the impacts that humans are having here on the islands that led us to do the research that we did. Josh is going to share some work on underwater navigation and why it's important for what we do. And then Mauka is the Hawaiian word for mountain. And so I'll talk about some of the work that we do on the terrestrial side of this. Josh will then talk about Makai, the ocean side of our research, and then talk about some of the implications for that. So one of the things that you'll notice if you spend any time driving around Oahu is that there are signs along the road that identify what are called ahupua'a. And ahupua'a are land management units that Native Hawaiian groups would manage, and so a individual population would work from the ridge tops all the way to beyond the reefs. And these ahupua'a, the name actually comes from a mound that looks like a pig. So ahu is mound, pua'a is pig, and these mounds would delineate different management units. And it's a really unique management style where it begins in the headwaters of streams, the water flows down. Most of the uplands are intact vegetation. As the water then flows down, it's diverted into flood irrigated agriculture that produce the taro that is used to make poi, one of the main carbohydrates sources. That water then continues down and along the coastal areas where the population was concentrated. Also at the outlets of these streams are something that's really unique in Polynesia, to the islands in Hawaii, where they have fish ponds, and these Native Hawaiian fish ponds are rock walls that encircle an area of the coastline, and they have gates on them that fish will swim in and they can't swim out. So it's a concentrating mechanism that brings the fish in and concentrates a source of protein for these communities. These ahupua'a vary in size, but they are large enough to sustain an individual community. An interesting thing happened with colonization, though. With colonization, with Europeans' arrival in Hawaii, there was a concerted effort to eliminate culture, and so it included the making illegal to speak the Hawaiian language, the elimination of hula and surfing, and so for a century or more, there was this desperate attempt to erase Hawaiian culture. Accompanying that was an erasure of the land management that was occurring, where the cultivation of taro was pushed to the margins, and instead there was a westernization of agriculture, where instead of being small-scale community-based agriculture, it became much larger, and we started cultivating crops that were much more destructive. And so where we work principally on the island of Molokai, first came in sugar cane. The soils were quickly depleted from that. Then came in large pineapple plantations. Pineapple plantations were no longer economically viable after a few decades. Then there was wide-scale livestock ranching that took place, and accompanying this was massive erosion. And as the soils were disturbed, the storms, if you were here yesterday, you saw what the storms in Hawaii can look like. And this is an example of one of the places where we work. This is a native Hawaiian fish pond. You can see the rock wall there. You see the crystal blue tropical waters on the outside, but within the fish pond, you see this iron-rich soil that's being deposited into the fish pond. In areas where there aren't fish ponds, oftentimes this moves out onto the reef. In the early 20th century, the Western companies recognized how damaging this could be, and so they brought in red mangrove. There are no native mangroves in Hawaii. They brought in red mangrove from the Caribbean, planted it out in attempts to capture some of this sediment as it was moving out into the ocean. These quickly escaped the places where they were planted, and now if you drive around all of the islands of Hawaii, you see this legacy of colonization in the mangroves. And so we see how changes that were occurring in the uplands quickly affected the marine system, and as Europeans tried to remediate, oftentimes they just brought in additional problems. In the early 1970s, there was a recognition that there needed to be a renewal of Hawaiian culture, that this legacy of colonial impact had to be reversed in some ways. And to me, what's so fascinating is how central navigation was to this cultural renewal. It was tied to relearning language, a return to old ways of agricultural cultivation, of renewal of fish ponds. But probably its most prominent manifestation was the Polynesian Voyaging Society, as a group came together and said, we need to return to the ancient ways of navigation to show the children in Hawaii this rich cultural heritage. And it was fascinating because the colonial impacts had been so pervasive that there wasn't a single elder on the islands of Hawaii who knew the old ways of navigation. And so they looked around the world, and they actually found a well-trained navigator in Micronesia, who was able to connect with young people, young individuals that were identified as potential navigators. And this is the Nainoa Thompson, who was the first Hawaiian in the modern times who was trained in ancient navigational techniques. So that became one of the central ways that Hawaiians were able to reconnect to culture. This led to voyages of rediscovery. And so an ancient deep ocean sailing vessel was constructed in the early 1970s, and by 1976, there was training being taken place by Mau, this Micronesian navigator, who was able to show them the ways of using ocean currents and birds and stars to navigate by. And this is an example. And the vessel that was made is named Hokulea. And Hokulea has sailed and continues to sail the Pacific Rim. And just last year, it sailed to Alaska and back. But this is a map that shows the voyage that took place between 1985 and 1987, where without using any Western instrumentation, they were able to navigate and sail from Hawaii to Tahiti to Aotearoa, New Zealand, and back through Tonga and Samoa. And as we visited with some of the navigators who navigate today, and they were sharing their insights, this is a quote that really struck me, and that this came from Mark Ellis, and he says, as we were asking about what it is that Polynesian voyagers do, and he says, in the light of day and the light of night, the navigator makes thousands of observations to make hundreds of decisions to answer just two questions. Where am I and what is my heading? Which is the question that I think all navigators ask. How do I localize myself, and how do I know where I'm going? And the approach that the Polynesian navigators use are diverse, that they're using multiple data sources, and they range from the transition from night to day or day to night as the sun is low in the sky. The sun makes a line across the surface of the water, and with that line you can calculate angles against the swell that allow you to make inferences about direction based on the ocean surface. Celestial navigation has always been a central part of it, and so being able to identify where stars rise and where they set is a major part of it. Certainly, what happens at the horizon with clouds, and we'll talk a little bit more about that. But natural history was a central part of it as well. So understanding birds that are land-based and their ranges, and so you can do ranging based on which bird species you find and which direction it is flying depending on the time of the day. And finally, what's happening at the surface of the ocean as well. So Hokulea derives its name from actually a star in the sky. And it's a zenith star. It's a star that when it is found directly overhead, it's found at 20.5 degrees north latitude. So it's found directly over the islands of Hawaii. And so as you sail towards Hawaii from the south, Hokulea moves from the northern sky up to being directly above you. And so Hokulea can be used as one of these central celestial navigation points. The challenge, though, is that it's easy to know what's directly above you when you're standing on land. But when you're on a rocking boat, it's much more difficult. And Nainoa, as a young man, was being trained by somebody from Micronesia who knew the southern skies really well, but wasn't familiar with the Hawaiian skies. He had never had to navigate using celestial navigation to get to Hawaii. And so as Nainoa was being trained up, he knew his challenge was going to be, he was going to be the captain and the principal navigator as they sailed from Tahiti back to Hawaii. And you can imagine the challenge that he faced, that you had this zenith star that would get you close, but how would you know when you got to the latitude you needed to be? And so here in Honolulu, one of the things that he did is he would go to the planetarium and ask the director of the planetarium to set up the night skies depending on latitude. And he would go home at night and puzzle it out. What are my signals going to be to know that I'm in the right place? And what he discovered is that as you sailed from the south to the north, the Southern Cross moved lower and lower in the sky. And when you got to that 20.5-degree north latitude, that was so important to know that you could then turn and follow that latitude until you ran into the island. He recognized that the Southern Cross stood at 6 degrees of latitude, and it sat exactly 6 degrees above the southern horizon. And so being able to use that was a secondary source of information. You could use zenith stars, and then you could use these stars along the southern horizon. And so as we have visited with these Polynesian navigators who continue to do such amazing work navigating, we were struck by how many of the insights that they had developed over centuries of navigation are the same questions we're asking today. And so I'm going to turn it over to Josh, and he can share some insights there.
All right. So one thing I really like from what Rick was saying is, as a navigator, the two main questions you're interested in answering are, where am I and where am I heading? Right? So for me, I'm trained as a roboticist, and so this aligns directly with what we call the robotic localization problem. Right? So the robotic localization problem is where you're trying to determine where you are, what's your heading, and what's around you, so that you can be able to really then plan a trajectory that will work in order to get to where you need to go. When we do this, there's a lot of different methods that we use to do this. One of the main ways that we do this is using what's called filtering techniques. I'm sure many of you are familiar with those. But one of the main goals here is to be able to track our position and track our uncertainty as we navigate, right? So we want to be able to know where we are and also how well we know where we are. So often when we draw pictures, we denote this using an ellipse. So you can kind of see that little ellipse underneath the vehicle there. That denotes how certain you are of your position. And we want to be able to take into account uncertainty as we traverse, right? So as we get measurements, typically if you're navigating, you may get measurements that we often call odometry or dead reckoning that give you an idea of how you're moved through space. And you can use those measurements to predict and propagate forward your position and state, and then get a new update for your state and a new position estimate. One thing that's interesting when you do that is your uncertainty typically grows because you have some measurement of your motion, but you might not have actually perfectly followed that, right? So the ellipse grows there, and you can see higher uncertainty as you do that. And we can continue to do this, right? In a filtering, this is often called our motion prediction step, or it's a step where we're trying to predict where we are in space after we've made some motion. But as you continue to do that, your uncertainty is going to continue to grow until you get some global measurement of some kind, right? So if you get a GPS measurement, the GPS might tell you, hey, I think you're here with this air. And then if you fuse those measurements, you can get a better estimate that combines those two uncertainties, right? And this in filtering, this is often called your measurement correction step, the Kalman update if you're using a Kalman filter, or a sensor fusion step, right? Where you're taking two estimates of your pose and you're fusing those to give you a new estimate that's updated, including all of that information. And then you can continue to do this, right? So you can continue to propagate, you can iterate between these two steps. If you get new measurements, you can continue to combine those and move forward and keep track of your state estimate. If you have prior information about your environment, you can use that as well, right? So if you have a map of your prior environment, let's say that map gives you the location of landmarks that you can somehow recognize using a camera or some other sensor. As you navigate through, you can propagate your motion in the same way that you normally would. But if you then get range or bearing measurements to a landmark, you can compare that range or bearing measurement to what you would expect from the map and where you thought you were. And then you can correct your state using that, right? One of the really cool things about this is it actually bounds your error, right? So if you get a global position or an absolute measurement like this of something that doesn't move, and you continue to get those measurements, you can actually make sure your error doesn't grow above some bound, right? Because if you just continue to motion propagate, your error will grow unbounded. But as you get global estimates, you can actually constrain that to be a fixed total error or maximal error. One of the things that we work in my lab is what we call simultaneous localization and mapping, or SLAM in robotics, where you're trying to estimate your pose by using landmarks like this, but you don't have a prior map. So let's say you don't have a prior map as you're navigating through the environment, you simultaneously need to find landmarks, determine where they are, and then estimate how they influence your state. And so it's kind of a chicken and the egg problem, which tends to be tricky, but it is a really interesting problem to be working on. So I run the Field Robotic Systems Lab at BYU. We really take these algorithms that I just mentioned before and variants of them and apply them to marine robotic systems, right? So most of the work I'm going to be talking about is really done by all my students at BYU. So I want to thank them and acknowledge them because they're awesome students. So, but here's a picture down here that we just took 3 days ago from 45 minutes north of here at Kahana Bay, where we're doing some testing actually the last week, and this next week we'll be doing some further testing there as well. It's all over Oahu actually. So what we really apply these things to is underwater vehicle navigation. And underwater vehicle navigation is really interesting because it has very unique challenges, right? So underwater navigation is inherently GPS denied. So in air we talk about sometimes there's GPS denied conditions, but as soon as you get 6 inches underwater you lose GPS. So you no longer have the ability to use that as your main reference for a global position estimate. Another thing that happens, you can kind of see in this picture that's just starting here, is often due to particulates floating in the water, we get turbidity. And that turbidity is going to vary depending on where you are and the weather and the conditions. But often you can barely see underwater. That vehicle is 2 feet in front of the camera, right? So you can't actually see very far in these conditions. If you get low enough in the water, then light doesn't travel enough and it gets dark. So visibility can be really, really low. Highly constrained communications happens as well for the same reasons that the GPS doesn't work, right? So as soon as you get 6 inches underwater, your EM signals cut out, and you no longer have radio connection to the vehicle. So there's a lot of factors here that kind of tie in and make it an interesting problem to be working on. This last one shows kind of this example of a priori unknown environments that we deal with as well. Typically in a marine environment, you have some rough idea of where you are. You know, maybe you have a bathymetric map, but that bathymetric map is really, really coarse. So here you can see an example of a rock that wasn't in the map, right? And so the vehicle had a hard time. It was trying to avoid, but it couldn't surface fast enough to avoid that. And these underwater environments, because we don't typically operate in those spaces, they're outside of our normal experience. So it's often difficult to see and predict what it'll actually be like when you get down there. But as we're working on these things, when we first got here to get started on some of the Molokai work that I was involved in with Rick, we came through Oahu, and we stopped and talked with Mark Ellis that Rick mentioned earlier on, and he took us to go visit Hokulea. So we went to the University of Hawaii Manoa and visited Hokulea while we were there, and we talked with Mark about the navigation techniques that they used when they circumnavigated the world. And it really struck me the similarities between what they did and what we try and do now, right? Like we're trying to develop robotic algorithms that enable us to do the same things that they've done for thousands of years. I want to kind of just dig into how what I talked about the last several slides ties into what they did in order to do navigation. So one of the first things we talked about was dead reckoning, right? So dead reckoning is kind of this idea of getting a measurement of your own motion over a short time window or time sequence of time. So typically when you do that, you need a heading and you need either a translation or velocity measurement of some kind, right? So the way that they actually did this, one of the main ways that they'd be able to track their heading was to use currents if they were nearby the islands. So here's an example of a Marshallese stick chart, and Native Hawaiians have the same type of concept, where you'd build these stick charts. They wouldn't take them with them. This was really just a memorization tool. So they would memorize where all of the islands were and where all of the currents were in between those islands. So each of these sticks represent currents, and each of these little shells represent islands in the Marshallese Islands. And you're trying to keep track of, memorize where those are, and then when you're out on the water, if you feel or detect that current, you can then use that as a reference of your heading relative to the islands nearby you. even if the islands are too far for you to see, right? They'd also do directions of swells, so similar to what Rick was saying before. When the sun was rising or setting, they could find east or west, and then they could detect the angle of the swells relative to that. And if you hold that constant, then you now know your heading, right? So you can use that as a reference as well to keep track of your heading. In terms of velocity estimates, they would determine when the crests pass the bow of the canoe, and then when they pass the stern. And by calculating that time or keeping track of the time, they got an estimate of how quickly they were moving through space. So this gives you an idea of how they could do dead reckoning. In terms of global position and heading measurements, they would use celestial navigation. Right? So celestial navigation, as Rick mentioned, one thing that's really, really cool about stars is they're fixed relative to the celestial sphere of the Earth. And so because of that, at a given latitude, they rise and fall at the same places. So over the season, they might change what time they rise or fall, but they always rise and fall at the same places at the same latitudes. So because of that, they built a system like this, which is really just a tool they had in their heads written down on paper, right? But what they would do is they would track, this is north, this is south, east and west. And they would track when stars rose and then when they fell. It went below the horizon, and from that they could orient to determine where they were in space. As Rick mentioned, there's also you can also get latitude observations from this, right? So if a star happens to go directly overhead, that's your zenith, then you can actually use that to be able to get what's called the declination of that star. So from the declination of that star, you can determine where you actually are in terms of latitude. One thing that's interesting about this, though, is it's really difficult to actually track that long term, right? If you're rocking on a boat, it's really difficult to find what stars go directly overhead. So this compass also works in the same way, right? So a star that goes directly overhead will rise and then go in a straight line over the top. So if you see a star that curves, it means you're not at that latitude, at the latitude that affects that star, that it corresponds to that star. So what they would do is they would sail until they found that correct latitude, and then they would turn east or west, and they would follow that until they actually got to the island. So they would know which latitude or which stars or zenith stars for those specific islands, and then they would follow those trajectories. Okay, so then that's what you can do at night. But what about the whole time that you're there in the day, right? In the day you can't see any of the stars. So what they would do is they would do landmark-based estimation in a similar way to what we try and do now, right? And the really cool thing is they could actually do this over the horizon. So they didn't need to be able to see the island physically. They could actually determine where the islands were from a bunch of other signs. And I want to go through some of those here quickly as well. As Rick mentioned, by bird species, they could, if they found terrestrial birds, they could determine how far away they would be from land. Because certain birds fly a certain distance from land, and so based on the species of bird, they could determine I'm 100 miles or 100 kilometers from land, or I'm 30 kilometers from land, based on what the species of bird was that they observed. In terms of bearing measurements to islands, they could use cloud formations. So sometimes the islands themselves are not visible because they're below the horizon, but there's certain cloud formations that will form over the tops of the mountains. And so from that, you can actually, if you can observe and detect those cloud formations, you can detect over the end of the horizon where the actual island is. Sometimes the islands are too small to be able to see, but you can actually see the islands reflecting themselves or being reflected in the clouds as well. So this is a picture from outside my hotel in Laie. One of the things that Nainoa talked about on his trajectory back, when they had reached the right latitude and they were trying to arrive at Oahu, was detecting changes in color of the sky and the sunset. So they had sailed north and they were trying to sail west to arrive at Oahu, and the sun was setting, and in the sunset he could see like a difference in colors, where it was bright on two sides, but in the middle it was dark. And that was the shadow of the island actually reflecting and causing an effect in the sunset, so he could get a bearing measurement to where the island was from that. And that was the date that they arrived on Oahu. Similar things, changes in wind. So the wind will typically follow general patterns, but when it hits a mountain, it has to split. And so by those difference in changes in wind, you can actually get a bearing measurement to where the island is. And then directions of birds as well. So with these land-based birds, if birds are flying towards a certain direction at dusk, it probably means that land is in that direction, right? And at dawn it's the opposite. So they can actually use that as a way of doing bearing without even being close to where those islands are. So I'm going to hand it over to Rick here, who's going to talk about some of our work in the mountains and
So the work that we did with Ainamamona was in a watershed in one of these ahupua'a on the south shore of the island of Molokai. And here you see what it looks like, where you've got the Native Hawaiian fish pond down at right at the coastline there. You actually can see a couple of shrimp farms there that show sort of an additional legacy. That they started doing agriculture adjacent to the fish pond there, and then as you go up the mountain to where we're looking, you see this area that is now principally used for livestock grazing. You can see the road that comes up the mountain that's there that supports the grazing operations. And what they were recognizing is that they had spent years and years restoring this Native Hawaiian fish pond, and every time a big storm came through, it got filled with sediment that was coming off the mountain. And they said, can you help us understand the sources of that sediment and how to do something about it? And so this is the watershed. On one side it's grazed, on the other side it's not, and I'm not going to talk about that too much. But on this heavily grazed side, where they're wanting to do some interventions, we've got some ground control points that were established. And in 2019 is the first time we flew this with UAVs. We flew it again in 2021, aligned those images. And the first thing that we were interested in doing is just some simple change detection. Where did we see changes in land cover in just 2 short years? And here the red shows places where it was classified as bare earth in 2019 and again in 2021. You may not be able to see it that well, but there's a number of areas here where it changed from low vegetation, so grasses, into bare earth. And there's some yellow spots through here where we had shrub cover that changed to bare earth as well. What's particularly important, though, is the change in our surface, right? And so we developed digital surface models from 2019 and 2021, again, where you see things turning darker red. This is places where we saw net deposition. Where you see things in the yellow, this is where we see net loss. And when we sum the volumetric difference of this entire landscape between 2019 and 2021, what we saw is the movement of about 5,000 cubic meters of sediment. Some of that was moved within the landscape itself, but far more important is that there was a net loss of about 2,000 cubic meters of material that was lost out of the ahupua'a system. We used our digital surface model to look at water flow, to identify where there were major stream courses, especially in areas where there had been a net loss of materials, and with that be able to advise the community on where they can go in and put in barriers to the movement of sediment to reduce the movement off of the landscape. And so that's one way, and one of the things that was really fun, though, is to work with Walter Ritty, this 80-year-old Native Hawaiian activist who has been active in the Hawaiian sovereignty movement, and he was so excited to be flying UAVs with us, and to send them maps and say, hey, here's places where you can step in and intervene and stop the movement of sediment into the reef.
right, so now I'm going to talk about some of the things that we did on the marine side, under the same project that Rick just talked about. So as Rick talked about, there's this large amount of erosion that's happening on Molokai. And this is a problem because Molokai is home to the largest fringing reef in the United States. And that fringing reef is actually still used by the Native Hawaiian population on Molokai for subsistence fishing. So it's a really important resource that it's essential that we try and maintain. And this sedimentation is actually running down into the reef and destroying the reef, and it has been for decades. So this is something that we're really interested in. One of the people we were talking with, one of the Native Hawaiians there on Molokai, he talked about how he would, as a child, he would go around and the water was perfectly clear, and now it's just completely muddy. And so there's a huge difference that's been going on in this case. So the first thing we were thinking about is how do we actually sample this? How do we actually determine what's actually happening and where is this happening? And so here's a picture of one of my PhD students and one of Rick's PhD students collecting sediment samples off the coast of Molokai. But this manual sampling is time consuming and costly, and it's really difficult to scale. So one of the things we've been thinking about is how do we automate this process and make it so that we can scale it to much larger environments and much larger with limited amount of time. How do we ensure that we can actually do this at a regular pace? So our first thought and our first cut at this was to take an autonomous surface vessel, outfit it with stereo cameras, RTK GPS, and water quality sensors. And this is a video of it running in November 2021, where we're trying to actually build some 3D model in the same way that Rick did in the air, but underwater in this case. So the stereo cameras, they have GPS at the surface, and then we're able to collect the position information from that, and then we can get camera data below the surface to be able to build these 3D models. Here's just another GIF of that. You can see kind of the scale at which we're operating. So the vehicle moves around, it's trying to collect data in an overlapping pattern so that we can try and build these 3D mosaics. Here are 5 different sites off the coast of Molokai where we've done this testing. And so each of these sites is about 30 meters by 50 meters in size. And then because of the stereo camera imagery, we can build a full 3D reconstruction of those sites. Here's like another angle of it, but if you zoom in, you can actually see individual coral heads in these reconstructions, right? So we can actually count the coral heads. But one of the things that's really, really cool here is that we can, because this is a 3D model, we can get a measurement of what's called rugosity. So rugosity it's a measure of the complexity of a 3D environment or a 3D structure. And that rugosity correlates directly to how healthy the coral is. So if you have healthy coral, you're going to have high complexity because there will be lots of corners, lots of angles, and lots of different growth in different shapes. If it's turned into rubble and sand and starting to die, then it will just be flat. And so you can kind of get some measurement of the rugosity from this, which is really, really exciting. We've also more recently been working with on the island of Oahu with BYU Hawaii. So we're with BYU in Provo, but BYU Hawaii has a really strong marine ecology group. And BYU Hawaii is about 50 minutes north of you right here in Honolulu. So we've been working with them. The Polynesian Cultural Center is also run by them, so if you have time, definitely go up there. We've also been working with Kuleana Coral Restoration, which is a nonprofit coral restoration group run out of Ko'olina that's trying to find damaged corals that have been broken off by storm surges and then replant them so that they can try and keep the ecosystem healthy. So we've been working with both of them. We came back last year in 2023, this time brought underwater vehicles and a surface vessel and mapped 9 different sites around the coast of Oahu. The underwater vehicles, they have stereo camera, and so that we could do the same type of work as what we did with the surface vessels on Molokai. But we can go much deeper and at much larger scales than we could with the surface vessel. So here's some results from that. This is a 3D reconstruction of the Mahi shipwreck, which was actually sunk as a way of trying to create a man-made reef, right? So it was sunk in so that we could try and get structure on the seafloor in the hopes that it will actually grow and support fish and coral life. You can see some camera imagery we've collected from that, and then this is side-scan sonar data using sound to actually image that shipwreck as well. Here's a couple more examples of coral sites that are actually that are directly tied to where Kuleana is trying to operate, where you can actually see individual coral heads in the 3D reconstructions as well. And we're actually here, we've been here the whole last week, and we are here the next week as well, working with our graduate students and undergrads, collecting more data in connection with Kuleana over since last year. Our hope is to be able to do really time series changes where we can actually build a 3D model of one of the restoration sites and then come back a year later and remap the entire same site and be able to see the difference between those two. So in terms of future plans, we're continuing to work here on Oahu as well as on Molokai, trying to do time series monitoring of these restoration sites. We're working with BOE Hawaii, trying to collect an understanding of how this is affecting the fish populations as well in those communities. And then on the robotic side, we're interested in AI and localization algorithms that enable these robotic systems to really understand what scientists and conservationists need and be able to be more easy to use. Right? So these are some of the things that we're working on in the short term here as well. So I'm going to hand it over to Rick here for the last section.
And so I just wanted to finish up talking about something that Nainoa Thompson talked about quite a bit in his training. He talked about how Mau as a navigator was always going to be a better navigator than he, because from the earliest age, Mau was being raised up to be a navigator. He tells stories of his grandfather taking him as an infant and setting him into tide pools so that he would get the feeling of the ocean. And he Mau also told stories that as a young man, 5, 6 years old, his grandpa would take him and tie him while he was on the canoe and throw him off the back so he could get the feel of the waves as they moved along. And so he was fully immersed in this system from a really young age. And there's opportunities now in the field of navigation, and especially among the Polynesian community, for an intersection between cultural renewal and a connection to STEM fields. And one of the things that's happening now in a number of places in Hawaii is trying to connect young people to a vision of them becoming navigators themselves. And they say, what exactly is the disposition of a navigator? And this is particularly telling in this audience. Well, what does it take to be somebody who understands navigation? And they talk about how, on these voyages, the navigator themselves wasn't the only one on the boat, right? That there were others that were voyagers, but to be the wayfinder meant something different, because the wayfinder had to have a vision of where they were going, that it wasn't somebody who was just following along. They had to have something in their mind that showed them where they needed to go. They had to be attentive to the details. That it turns out that on these weeks-long voyages, oftentimes the navigator won't ever go below deck to sleep. They will be on deck 24 hours a day. And they may close their eyes, but they have to be up there feeling the wind and feeling the waves. So they have to be able to pay attention. There has to be a reason for them to go, right? That there has to be purpose in life. For them to go from place to place. And they have to have that Mau-like immersion in what it is that they're doing. And so it's one of the things that we're really committed to do in the work that we're doing is to connect with young people on the islands and to introduce them to principles of robotics, at the same time acknowledging the power of the Polynesian vision of voyaging and wayfinding. And Nainoa, as he was trained up, he said one of the things that most impressed him about Mau was that Mau had what he called the magic, the ability to wayfind even when some of these landmarks weren't visible. And it makes sense that when you can see the full night sky, that you're going to be able to use celestial navigation as a way to connect. But one of the things that Thompson recognized is that as he made his way from Tahiti back to Hawaii, that he was going to have to deal with the doldrums, this space in the open ocean where it's going to be cloudy all the time, and these landmarks aren't going to be visible. And it's going to look something like this, and then it gets darker and darker. And he tells this story of just how troubling that was to him, to know that there was going to be at least part of his voyage where he wasn't going to have access to all of the answers. And he, in his recollection of navigating to Tahiti, the voyage that they took in 1980, he told of what happened as he puzzled and as he wrestled with what he was going to do without landmarks. And he says finally he just gave in to a knowledge of the system that he had. And he says, when I gave up fighting to find the moon with my eyes, I settled down. I suddenly felt this warmth come over me, and I knew where the moon was. The sky was so black I couldn't see the moon, but I could feel where it was. From the feeling of warmth and the image of the moon came a strong sense of confidence. I knew where to go. I directed the canoe on a new course, and then, just for a moment, there was a hole in the clouds and the light of the moon shone through, just where I expected it to be. I realized that there was something very deep inside my abilities and my senses that goes beyond the analytical, beyond seeing with my eyes. I cannot explain what this is from a scientific point of view, but it happened. And now I seek out these experiences. I don't always have them. I have to be in the right frame of mind, and beyond that, internally, I have to be able to enter into a kind of spiritual realm. I don't want to analyze these experiences too much. I just want to make them happen more often. There are certain levels of navigation that are realms of the spirit. And it's such a beautiful way to capture this idea that the insight that we hope that we get as scientists, as engineers, where we are so immersed in the systems that we're part of, that there are these aha moments that come to us, these moments of realization. And one of the great challenges that we have is being able to provide those for our students and for the rising generation. And I think that's the challenge for all of us. And when we become immersed in systems that are scientific and technical and cultural and environmental, I think that we're much more likely to get these and be able to share them with others. And so with that, we'd love to take any questions that you have. Thanks.